Hi everybody, it's a pleasure for me to have this opportunity to share with you. I'm going to talk about testing of fusion categories from quantum groups of type A. This talk is based on my master thesis, which is also a continuation of the paper Brady's testing and its applications by Colin Delaney, Julia Plumnick, Eric Rowell, Kim Chang, and Cesar Galindo, where they introduce testing as a new way to construct a new fusion category from a given fusion category by changing its fusion rules. Here by fusion rules, I'm talking about the way that we decompose a tensor product of two simple objects into a direct sum of simple objects. Okay, now my interest on this work is very concrete. I'm going to describe all the braided testing from a very specific fusion category, that is the fusion category SUN level K, which is obtaining from a quantum group where I'm taking Q to be a root of unity of order 2L, where L is this number, n plus K. Okay? First, I will introduce some notation that I will need. First, by C, I will denote a fusion category. I'm going to use this notation here for the set of I subclasses of simple objects of my category. In a similar way, I will use this notation here for the set of I subclasses of invertible objects. Here, the notion of invertible objects are like this. An object is invertible if I have isomorphisms when I take the tensor product with its dual. This tensor product is isomorphism with the unit object of my category. Okay, also I will need this notation here. When I have a subcategory of my category C, I will denote by this the relative centralizer of my category, and also I will use this notation here for the category generated by all the invertible objects of my fusion category C. Now I'm going to talk about my example of fusion category, the fusion category SUN level K. Here this category is obtaining from a quantum group of the enveloped algebra of SLN, where I'm taking Q to be a root of unity of order 2L, fixing that L equals to n plus K. We have two descriptions of the simple objects on this category. The first description are in terms of n minus 1 integers, that its sum is less or equal than k, or that its sum is equal to k if I have n integers. But the description I will use most on this work is in terms of Young diagrams. A Young diagram that fits in a n minus 1 times k rectangle. So for example, here I have two Young diagrams, the diagram 3, 2 and the diagram 4, 2, 1. Here we can view these diagrams as simple objects of the following categories, as the following at the category SU3 level 3 and also for SU4 level 4. Okay? Now I'm going to give a very known description of the invertible objects of my category. The invertible objects of SUN level K in terms of Young diagrams correspond to diagrams which have K boxes in each row. So we will have a generator for the group of invertible objects that corresponds to the object that correspond to the object of the Young diagram of one row and K boxes. Okay, I will denote this object by sigma. So for example, we have the simple objects of SU3 level 3. The simple objects in terms of the Young diagrams and partitions of 3 are this. Here, the invertible objects are this one that corresponds to sigma, diagram with one row, 3 boxes. This corresponds to sigma to the square. And this is the identity object. Okay? Now I will need the concept of a G graduation for a fusion category. When I have a finite group G, a G gradient for my category, for my fusion category is a decomposition of the category in terms of a direct sum like this, where I have the following. If I take the tensor product of two elements in a graded component, in two graded different components, the tensor product will be in the component graded by the product of the two elements of my group. Okay, now with this, I will give the example of the graduation of my fusion category SUN level K. We have a CN graduation for this category that is given by the number of boxes in the Jones diagram associated to the object in this category. Here I'm taking the number of boxes mod n. So this induces a graduation for my category. Okay. Now, with this in mind, I can talk about what is an associative zesting. So an associative G-zesting lambda for a G-graded fusion category C consists of the following things. First, we will need a map that assigns to a pair of elements of my group an element here in the category that basically is an invertible object in the trivial component of the graduation of the or the component graded by the identity element of my group. Here I'm taking all the invertible objects and I'm taking objects in the relative centralizer. Okay. Also, I will need a two-cocycle that is an isomorphism of this way of these two assignations of lambda that I will use some graphical calculus to represent. I will represent by this diagram the way that acts my isomorphism lambda from going from these labels to these labels. This in mind, I will need the following conditions for an associative zesting. First, these conditions with the identity of the group. Also, this condition here with the identity, and the following equalities in the figures will hold. These conditions are compatibility conditions that two different ways that we go from these labels to these labels are equal using the isomorphism lambda in different ways. So here, the important thing by defining this associative zesting is that a result from the paper of grading zesting as application is that when I have a finite group G and I have a G graded fusion category, if I have an associative G zesting lambda for my category, we can define a new G graded fusion category that such that the new tensor product in this category is given in the following way. When I take two elements in a component graded bar G1 in a component graded bar G2 and I take his tensor product, we have the following. First, I will use the tensor product in my original category, but I introduce a new element that is the invertible element in the trivial grading that we have in the associative zesting. So when we define this, we have a new fusion category with a new associative constraint that is given by the following definition. Using graphical calculus, we have the associative constraints in terms of the isomorphism lambda that we define in the system. Okay, and now I will classify all the possible associative zestings of SUN level K. First, I will need a number epsilon that is equal to 1 if these conditions hold, or is equal to 0 in other case. I will use this notation here, sigma n, for a root of unity of order n. Okay? So the classification of all the possible associative zesting of SUN level K are the following. All the possible zesting are parameterized by this group Cm cross Cn, where n is the level of my category, m are these numbers here, And we have this description for the associative testing. These first descriptions shows the way that I associate the map lambda from G cross G to the invertible objects in the trivial component of the gradient, and this assigned here that is labeled by the pair B by the component B is the two cocycle that we will need for the isomorphisms in the associative testing. Okay, now I'm going to talk about braided testing. So first we will recall that when I have a fusion category, we have two abelian groups. The abelian group of tensor automorphisms of the identity functor, and also we have the abelian group of tensor automorphisms of the identity functor, such that we have that for all the objects in the trivial component, we have that the isomorphism acts as the identity. Okay? With this in mind, I can define an isomorphism Xi in the tensor automorphism of the identity that is given by the equality in this diagram. I will use this isomorphism to define a braided testing. So with this in mind, I define what is a braided testing. When I have a fusion category, a braided fusion category B, that is graded by an abelian group A, we have the following. A braided testing for that category consists of a pair lambda T, where lambda is an associative testing, like we said before, and T is an isomorphism for each G1 and G2 that belongs to my group, is an isomorphism between these two assignations in the testing. And I have some conditions here, some structure conditions. First, these isomorphisms will belong to the group of tensor automorphisms that acts as the identity in the trivial component. And also I will have that for each of these objects in these graded components, I will have the following equalities in the figures. This is the way I will denote my isomorphism T using my graphical calculus. So I have these two. These first condition are ways that we go from these labels to these labels using the isomorphism lambda and the isomorphism T in two different ways. And also I will have this other condition here that is from going to these labels here by using lambda T, but I have this scalar that is given by my isomorphism Chi that I defined before. Okay, so the result of the paper of braided testing and its application is when I have a fusion category and a braided testing for that braided fusion category. The new category obtained by an associative testing is also a braided fusion category when the braiding where the braiding is given by the following isomorphisms in this figure. Okay, here I define what is the braiding for my new category, and is given by using the braiding in the original category and the isomorphism T that we have and the definition of braided testing. Okay, now I'm going to describe what are all the possible braided testing of the fusion category SUM level K. So when I have an associative testing that belongs to CM cross CN, we have the following. This associative testing admits braided testing if and only if this condition here holds. Here I'm using the number epsilon that I defined before. Also, we have that there exists n different braided testing that are parameterized by some number s, with that number s satisfying this equality here. And also with that number s, we have that the isomorphism T in the definition of braiding testing will act like this depending on my number s. Okay, so for example, if we talk about the associative abraded testing for my fusion category SU3 level 3. For this case, we obtain 9 associative testing parameterized by this group C3 cross C3. Here we have the way that we associate to appear in the group elements in the invertible objects in the trivial in the component graded by the identity of the group. And here we have the description of the two cocycle. Also, we have that this category admits a braided testing if and only if this condition holds. So we left to only 3 possible pairs of numbers in my group, in my original group, the pairs 0, 0, 1, 2, and 2, 1. And for each of these pairs, we have 3 different values of S that admits a braided testing for my category. Here we have, for b equals to 0, we have these 3 possible values. For b equals to 2, we have these 3 possible values. And for b equals to 1, we have these 3 possible values. Okay? So this is the biography that I use, the paper of braided testing and application. That's the biography in my master thesis. So thank you very much.